Start recording. Okay. So if I now look at my Levenspiel plot, where I plot the inverse of, okay, that's now, there's my negative, inverse of the right. So tune yourselves, low is high. If I have a low value here, I've got a high right as a function of conversion. So if I had an isothermal elementary reaction, and I plotted min RA, K, CA, whatever that stoichiometry is, if this stays the same, there will always just be a decrease in the rate because my concentration will be equal to FA naught 1 minus X divided by Q. So as I increase X, there's going to be a decrease in the concentration. If the concentration decreases, the rate is going to decrease. So for the isothermal case, where I had a constant K value, it will start at the highest rate where my concentration is the highest, and there's just going to be a decrease in the rate, a monotonous decrease in the rate as I increase conversion. But now what happens in my rate equation is, if I look at min RA, it is now, I must remember that this is E over RT CA squared. This is still a function of X, and it's still going to decrease as X is going to increase. So as conversion proceeds, this part of my rate expression will go down, and it will want to result in a lower rate. However, if I have an exothermic reaction, if I just consider my temperature from the energy balance as a function of X. So now, let's just consider that graph. So if I have my temperature as a function of X, for an exothermic reaction, all of you got this positive slope. So as I increase X, I increase the temperature. So with an increase in temperature, this term wants to go up. So I've got two competing effects, and this is often where we find ourselves in a design situation, is that we've got an effect that is, it wants to improve the rate, this one decreases, and it's nothing I can do about it, it's just this nature of the energy balance and the rate equation, its function of concentration. Nowhere did I say because it was in a CSTR, nowhere, or in a PFR. It's just for a specific value of X, I can calculate the concentration. For a specific value of X, I can calculate the temperature, and therefore I can calculate my rate. So what happens? This dependence is exponential. So the rate depends exponentially. There's an exponential increase in temperature. And the higher your activation energy, the more pronounced that effect. Right. So initially in an exothermic reaction, what originally happens is I will start at a rate. And instead of this concentration effect resulting in a decrease in my rate, the rate will increase even though my concentration is decreasing. And why is that? It's because of this exothermic nature of my reaction. So I will have a decrease in the rate and then up to a point, and then the concentration effect is going to start dominating, and then only does the rate start to decrease. So typically for exothermic reactions, you do observe this minimum in the rate, and this where this lies depends on combination of things. What is the size of your activation energy? How temperature dependent is your rate? What is the size of this slope? By how much? So therefore the del H of your reaction, by how much does the temperature increase with X? Etc., etc. Right. And of course, if the concentration dependence, if it's just a Ca there or a Ca squared, this moves this position where the concentration effects start to dominate. But that is what happens for an exothermic reaction. So now for an endothermic reaction, with X, if I now consider that same rate equation, times Ca squared. What happens? As I increase X, I will see a decrease in the concentration. But if I consider my energy balance, temperature X, I will also see with X, I will see a decrease in temperature, right? So for a specific conversion, sorry, I'm drawing this figure wrong. So it's X temperature, I'm sorry, X temperature for the endothermic and X temperature for the exothermic, right? So for the endothermic reaction, if I have an increase in X, I have a decrease in my temperature decreases. So this term will also decrease. So I have the two effects working in the same direction. So for an endothermic reaction, I will see similar type of shape than for an isothermal reaction. It's just going to be more pronounced because I've got the additional effect of the decrease in temperature with concentration. Questions on that? Okay. Thank you. Try this. Plot this. So in any of your two tats, change the sign of del H reaction from positive to negative and plot your Levenspiel plots to see whether you agree with this.